Welcome. Let's take a look at an application of curves in space or vector valued functions. And the application we're interested in here is where two curves might intersect. And so in this example, we're looking at two particles that are traveling in space along trajectories or paths. And these paths are described by vector valued functions as you see them there. And the question we want to consider is, do the trajectories or the paths of these two particles intersect? And if so, will the particles collide? So we're given our two vector valued functions, and these are our two trajectories. So if we think about what does it mean for the paths to either intersect or collide, what we're thinking about is that the two particles go through the same point in space. Now, they might go through that same point in space at different times, or they might go through the same point in space at the same time. So rather than look at the intersection idea first, let's start with the collision, because if the two particles collide, then they clearly, the paths intersect. Whereas if the paths intersect, the particles may or may not collide. So we're going to start with the collision idea first. And so what that means is if we look at the x coordinates, the y coordinates, and the z coordinates of these vector valued functions, for the particles to collide, the x coordinates have to be the same at the same time. The y coordinates have to be the same at the same time. And the z coordinates would have to be the same at the same time. So what we're going to do is we're going to look at what would have to happen for the function, the x function in R1, our position function 1, to equal the x component of function 2. And we'll start there. And so if that were to happen, what would be the case? Well, that would mean that t squared would have to equal 4t minus 3. Using some algebra, let's subtract 4t and add 3 to both sides of the equation. So we have t squared minus 4t plus 3 equals 0. It's a quadratic equation. It's easily factored. So that's t minus 3 times t minus 1 equals 0. And so the solutions there, if t is equal to 1, then that product is in fact 0. If t is equal to 3, then that product is in fact 0. So what we have here are 2 times 1 and 3, for which the x coordinates, the x component functions of the two vector valued functions are the same. Which then raises the question, okay, we've made sure that the x coordinate for the two vector valued functions are the same. For those times, will the y component functions and the z component functions be the same? Because all three component functions have to be the same for the particles to collide. So let's go ahead and take a look at our y component functions. So we could say if, let's start with t equals 1, then y1, so the y component function from our R1 would be 7 times 1 minus 12, which is negative 5. And the y component function from our second vector valued function is simply t squared, so that's going to be 1 squared. That equals 1. Well, we can clearly see that negative 5 does not equal 1. So what this means then is I know right away the particles do not collide. Now, we don't know that they don't collide. So now the question is, do their paths intersect? That is, do they go through the same location at different times? So we'll look at that next. And since we know that the 2 points, or the 2 particles, are not going through the same point in space at the same time, I'm going to change the parameter for our second function for this R2. I'm going to change the parameter to another symbol, another variable. I'm going to use S, so that I'm not tempted to think that t and is the same for both vector valued functions. Okay, so we're going to have our first trajectory, our parameter will be t, and in the second trajectory our parameter will be s. Now the process is going to be similar to what we did before. We need to arrive at the same point, at the same x value, but it might be at different values of the parameter or at different times. So what we're going to do is we're going to start by saying, well, if they're going to go through the same location in space, then the x coordinates would have to be the same for different times, but they would have to eventually be the same. So let's start there. And so we would have t squared equals 4s minus 3. The same would have to be true for the y coordinates. So y1 would have to equal the y function, that's the component for the y component function for the second vector valued function. So that would be what? It would be 7t minus 12 equals s squared. And then we'd look at our z component functions similarly. So z1 would have to equal z2. And so t squared would have to equal 3s minus 2. Okay, so what we've done is we've created basically 3 equations here that have to be satisfied. We got 2 variables, 3 equations, so we should be able to find the value of s and t. And looking at these, I'm seeing that probably the easiest way to do that would be to notice that we have a t squared equals some kind of function of x, of s, and a t squared equals some other function of s. Now those t squareds, that was parameters from the same vector valued function, so those t squared values should be the same. So here's kind of the big idea. Well, certainly t squared should equal t squared. All right? Whatever t is, for R1, those should produce the same value. For the x component, we know that t squared is equal to 4s minus 3. For the y component, we know that t squared is equal to 3s minus 2. So now we have a single equation in one variable s, so we can go ahead and solve for s. So subtracting 3s from both sides of this equation, we're left with s minus 3 on the left and negative 2 on the right. Adding 3 to both sides of this equation gives us s being equal to 3 minus 2, or 1. So now we have a projected value for s. We think that s should equal 1. And if s is equal to 1, then the x components and the z components should be equivalent. We do need to figure out what's happening to t. So if s equals 1, then that implies that, well, okay, so we could choose the equation we haven't used before, the 7t minus 12 equals s squared, so that's 1 squared, and solve that equation. So adding 12 to both sides of that equation would give us 7t equals 13, 12 plus 1 being 13, and t should be 13 sevenths, assuming that s is equal to 1. So t equals 13 over 7. So now we substitute into R1 the value of t we found, which was 13 over 7, and we substitute into R2 the value of s that we found, which is 1. So doing those substitutions into our first vector valued function, we would get 13 over 7 squared. Then we would have 7 times 13 over 7 minus 12, and then 13 over 7 squared again. If we simplify those, the x component becomes 169 over 49. The y component simplifies, the 7's will divide out, and 13 minus 12 is 1. And then we'd have 13 over 7 squared again, so 169 over 49. Our R2, substituting in 1, we would have 4 times 1 minus 3, 1 squared, and 3 times 1 minus 2, which would give us, let's see, 4 minus 3 is 1, 1 squared is 1, and 3 minus 2 is 1. So we can see that these two curves, these two vector valued functions, do not intersect. We can enforce the y components for them to occur at the same location, but we've discovered that there just really isn't a way for the x and the z components to coincide at these two different times, or for any two different times. So we would say that the two particles do not collide, nor do their trajectories intersect. If their trajectories were to intersect, then both of these vector valued functions would produce the same vector. I hope you find this helpful.